Started sharing.
Can you see the screen? I mean, can you see the?
I can't. Can anyone else?
No, it's still
Not
black.
yet. Oh, okay. So maybe I should. Oh, okay. Can you see now?
Yep.
Yes. Okay, let me try and. Okay, give me a moment. I'm going to try and get it into a slide show. Something is not all right.
I think it's the bottom right icon somewhere, Sanjeev. I'm not sure. I can't see
Yeah,
it.
there is. Yeah, there is. It's just that. Let me just. Okay, I'm going to restart it. Just to be. Okay, just give me a moment. Let me just start it again.
Yep. Excellent. Yep. All good.
Okay. Yeah. Okay, we are ready to go.
Excellent. So let me just quickly do your introduction and then we can get started. So it is our absolute pleasure to have Sanjeev Goyal here with us today. Sanjeev is a professor of economics and a fellow of Christ College, Cambridge. And currently he's a visiting professor of economics at NYU Abu Dhabi. Sanjeev is a fellow of the British Academy and a fellow of the Econometric Society. He was also the founding director of the Cambridge INET Institute and has been the chair of the Cambridge Economics faculty from 2014 to 2018. Sanjeev is a leading international scholar in the study of networks in economics, and he regularly publishes in top general interest economic journals. Today, Sanjeev will present his paper on learning in canonical networks. Sanjeev, welcome again. You have 1 hour and 15 minutes in total, including questions. You have the option of taking questions on the go or defer them to the end. With that, the floor is yours.
Yeah, so I mean, as is the norm in economics, I'd be happy to, I'd be happy if people ask questions along the way. I should say that we don't have a paper yet. We're writing the paper and so comments, criticisms would be, pen and paper would be especially welcome. We are just in the middle of working through the presentations. Let me start by thanking Girish for for inviting me to this seminar. Very happy to present. I must confess though that I've always wanted to visit the Waka, so I'm very sad that I'm not actually there in person. So, but I'm
maybe
hoping,
next time.
Yeah, so I'm hoping that this will not come in the way of another seminar in the future in person. So very happy to be here. And let me start by saying this is it's a joint work with Sinju Choi, who's a long-term collaborator, and Fred Mosson, who is in Lyon now. He was earlier at Cambridge. And Tony To, who's a graduate student, PhD student at Cambridge. And this is an experimental project, and it goes back actually to ideas I started thinking about when I was doing my PhD. So it really goes back to the early 1990s. And so it's been very nice actually working through. And today morning, I actually was trying to do some formal proofs and in preparation for this talk. So it's been very nice actually to get back to this, and it's been especially we'll see what you make of the paper, but with those, oops, no, I can't. Okay, so I think I'll have enough time to present this paper. There's not, it's a short paper, but just in case we run out of time. So this paper is about a fairly simple, but we believe rather important idea. And that is that, whether we think of markets or we think of politics, or we think about the way, society is organized, we have somewhere in the background the idea that whether you think about climate change or you think about, think about COVID, the science of COVID, that there are some facts out there, and somehow we may not always know these facts, but we could arrive at those facts, by putting together the opinions people have. So there's a sense in which, aggregation of ideas or competition for ideas, somehow is very fundamental to the way modern society is organized. Certainly, modern liberal societies are organized, and so underlying that is somehow the idea that people have disparate bits of information, and that institutions and processes are going to help put together, aggregate, collate this information, in a way that somehow would deliver good outcomes. So there's a wisdom of the crowd sort of idea, or the fact that somehow this information gets aggregated appropriately. Now, in many contexts where this is relevant, it turns out that not only do we have ideas, but we often talk to others, about these ideas or opinions, and then we form opinions based on our conversations with others. So it's going to matter who we're talking to and who the people we are talking to are talking to, or who they're exchanging messages with. So therefore, there is a presumption that the structure of the network is going to probably matter for the wisdom of crowds. Okay. So many of you in the audience are probably mathematically trained, and you can see that there is some version of the strong law of large numbers that's sort of underlying some of this. Okay, there's that sort of interpretation. But so the next remark is that, well, so if you want to think about networks, we're going to now think about communication, people sharing information locally. So now we're going beyond that simple strong law type argument. And so empirical work on networks has established a number of very striking properties of large communication networks. In particular, there are two properties. For instance, Twitter is a good example. So there are, most of us, for instance, I have a Twitter account, which I have not kept alive, but I think most of you who have Twitter accounts, you are like all of us, you have a few followers, but probably not more than 10, 15, 20 followers, right? On the other hand, of course, there are people like Trump, but also, Obama and so on, who have more than 100 million followers. Right? So these networks are extremely unequal, and this is quite a robust property of these networks. The other feature of these networks is that they exhibit homophily, which is the idea that, for instance, I'm a male economist and working, let's say, in economic theory. So most of the people I will be talking with will be typically men, will be economic theorists. Okay, so, and I'm interested in cricket, so maybe I have some friends through cricket. So I think, I think this idea that we, form ties with people like ourselves is very intuitive, very plausible, very, I think, natural, and it shows up in networks. So networks have this homophily property. Okay, so we have a few friends, and they are not randomly distributed in the population, but they mostly linked friends with people like ourselves. So the background to our experiment is this very powerful theory of opinion formation and learning, which shows that that these properties of networks, these unequal connections and homophily can have very powerful effects. Okay, so I'm going to talk about them as we go along, but the goal of this paper is to essentially have a background large network which is decentralized. People are mixing around with others, and then we will have, to contrast that, a network which is very unequal, and then we will have a network which is very homophilous. Okay, and we are going to see that in the experiment, this is with human subjects, we are going to see that indeed that homophily, this tendency of people to hang out with others like themselves, does lead to breakdown consensus. Okay, so there are facts out there, and people may disagree on these facts, even in the long run. Okay, so that's the first observation. That's a prediction of the theory, and indeed we find that is happening in the experiment. The second thing is that we look at unequal networks, and again we find, in line with the theory, that unequal networks lead to rapid convergence to consensus, but disturbingly, you can get a lot of incorrect consensus, okay, because you're following leaders who are actually misinformed. Okay, the final takeaway from this talk is going to be that behavior of individuals is very consistent with what is known as degroote updating. Okay, and I'll describe that. Some of you, I'm sure, are aware of degroote updating, but I'll come to that. So those are the three findings. And so let me now get into the main body of the presentation. So, so many of you have probably read this piece, or you've heard about this piece, and it's a piece by Francis Galton, who's a major polyglot, in turn of the 20th century in Britain, and he had this famous piece called Vox Populi, the Voice of the People. I think it's in Nature. And it's a one-page piece, and I really recommend that you read it. It'll probably, you can read it over coffee. It's just absolutely staggeringly well written, and it's very, very, very interesting. So what it does is it sort of surveys 800 people in this country fair in Plymouth, and it asks them, there's a ox which is being auctioned, and well, what's the weight of this ox, because it's going to be probably butchered and then sold, and so the weight is important to determine how much you should pay for the ox. So the point of this study is that there was different people guessed different weight, but the median guess was 1,207 pounds, which was roughly equal to the correct weight. Okay. So Galton then came up with this idea, and I think somewhere along the way, I think it's connected to the strong law. Of course, notice that in this, he was surveying people, 800 people. They were not talking to each other. Okay, so what he was simply saying is that when you're doing, people will have different views on factual matters, but if you put it together, you're going to get something close to the truth. Okay, so this is, of course, layman's way of thinking about strong law of large numbers, if you like. So this idea has been at the background in different ways, I think, of many different aspects of our life in a modern society. When you think of democratic politics, or you think about climate change, you think about COVID, you think about almost anything that we are, collectively we are interested in. Somehow the background idea is that you have to let people express themselves, you have to let people come to their own judgment of things. And there's a sort of presumption that if there's a free exchange of views, the truth will somehow emerge from this. Okay, that is better, even if it doesn't emerge, it's better than what the alternatives are. So it's important to understand somehow the circumstances under which, when people share information, when they talk to each other, that over time the opinions they will form will converge to the truth, if there is indeed such a truth in the background. Okay. Or it can be systematically, or they may not converge at all, or they may converge to an incorrect belief, a completely false belief. Okay. So that's the idea here. Now, let me sort of put things in perspective here. So we're going to be thinking about social influence, and we're going to be thinking about social influence without prices. Okay, so of course, as economists, we often think of prices as aggregating information, rational expectations and so on. So somehow, but this is going to be non-price. It's a non-price world. Okay, so if you like. So there's I should probably say that the study of social influence really goes back to the classical work of sociologists in the mid-20th century. Paul Lazarsfeld, Elihu Katz, and James Coleman and others, really laid out the foundations of this work, and they were mostly doing empirical work and showing, how social influence arises through in networks. I think it's fair to say that in the 1990s, with the launch of the World Wide Web and then online media, and in the last 10, 15 years, I think this has taken on quite a different life, and it's really taken on, there's this incredible, this very strong sense that social networks and the network structure of information is very important for understanding how societies function, how people come to have opinions in the way they do, and many of us are, of course, are quite, have been thinking about this, and there's been a lot of talk in politics. There's been a lot of talk about in the US, but there's also talk about vaccinations in the COVID context, and climate change and so on. So there's so many important sort of questions on which people feel social networks might actually be important. So just to fix our ideas, I mentioned this empirical research highlights two important features of networks. Twitter, for instance, as I said, there are a few 100 million people on it. The median person basically doesn't tweet at all, okay, and has essentially no followers. But then there are people with 100 million followers. So it's a incredibly unequal network, and this is not true just of Twitter. It's true, for instance, of the World Wide Web itself. It's an extremely unequal network, and indeed in our friendship networks as well. This is a feature of friendship networks. They are not so profoundly unequal, but still, they are very unequal. The other feature of social networks is homophily. Men mostly have male friends, women mostly have female friends. There may be linguistic boundaries. There may be boundaries based on race, and they are very important. And there's a lot of interest in, there may be boundaries based on politics. So in America, there's a lot of concern that people with a certain political predisposition mostly hang out with people with the same predisposition, so they can sustain out, extreme beliefs, because they never meet people who are, so there's that sort of idea. So it's been widely believed that these features, and so if you read the press, and in fact, even if you read rather serious books, there's a presumption that this is very important for the opinions people hold and how they make decisions, what sort of behavior they have. But scientifically to establish these effects is challenging, partly because if I'm talking to people like myself, the network may not be the cause, it might be the effect of the opinions I have, right? So it's not very clear. Identifying network effects is challenging, okay, because networks are typically endogenous. So therefore, people have started looking at exogenous networks, and started looking at testing these theories, intuitions, using experiments. So we want to do that as well. Okay. So I won't spend a lot of time on the literature, but I mean, this is being recorded, so you can probably take your time and go through this literature. But let me just say that in economics, there's been, certainly since the work of Friedrich Hayek, there has been a deep awareness of the role of information and the role of institutions of different kinds in putting together this information. And at least since Hayek, there's been this idea that markets work well because to the extent that they work better than other institutions, they do so because they allow people with local disparate bits of information to function, to somehow. And of course, this is probably not what Hayek had in mind, but rational expectations and the entire sort of tradition there is also, building on this, information revealing prices and so on. In the social learning literature, sorry, is there a question?
Yes, can I ask a quick question? This might be a trivial one, but so my understanding is that there was a theoretical literature which talked about how if you have two experts of the opposite opinion in a room and let them debate, it'll lead to a full revelation equilibrium. This is, I think, Battiglani or someone. So in some way, like both this homophily and the idea that many people, like there's inequality in networks, is kind of a manifestation of, or it's kind of related to that idea that, if you have two experts, that's a much better information set. But two experts of the opposite opinion debating, that's a much better information set. So for a person who is not an expert, I'll be more likely to follow experts. And since I'm not an expert, nobody will follow me. So that kind of is an equality in there. But also to the extent that I value unbiased opinion, or I value the full set of information, I will go for, so if I just want to be in an echo chamber, I'll go for experts of only one kind, right? So both those things seem to me as an offshoot of that literature, no?
So I think you're referring to agreeing to disagree type of work on the one hand, and then there is the strategic information transmission literature on talking to experts of different kinds. But there are two different strands. What we're doing here, in both those literatures, there isn't somehow, a lot of attention being placed on, they typically would have, they will have essentially, the mapping from that into a network model is not that straightforward. There is some work by, my good friend Andrea Galliotti and others, which looks at information transmission in network settings and basically asks, when you do strategic information transmission or you exchange opinions, repeatedly, how the network structure is going to matter. It turns out, I think that this is a high-level summary of this literature would be that it's still a fairly open problem. So the older work on experts or agreeing to disagree type of results, they don't pay a lot of attention to the network structure. And they don't pay a lot of attention to these features, inequality in connections and the homophily. So I won't actually talk about the theory a lot today because of, the focus is on the experiment, but what's really going on in these network models is somehow that underlying a lot of what is going on in these models is that when you have very different sort of heterogeneous connectivity across people, essentially what it does is information that different people have gets weighted very unequally. And eventually if the network is connected, everyone's going to hold the same view, but how much weight everyone's going to have in that final view is going to depend on their location in the network. And depending on the model you're looking at, roughly what happens is that people who are very highly connected will have more weight in this final view. And therefore they can bias the opinion that society will have. So that is in a setting when you do get consensus. Okay, but of course you can have breakdown of consensus because people simply stop listening to each other. Okay, and typically those kinds of things happen in settings where people are not fully rational. Now that is because, you know, the models with full rationality have not really been solved in networks. They become intractable. And so I'm giving a very crude sort of thing, but at a high level, if you do get consensus, the speed at which you will get consensus will be shaped by the network. And if you don't get consensus, you get breakdown, that's shaped by the network.
So quick follow-up question.
They are basically mostly been studied by network theorists. And because the problem is so hard, they have typically been studied in boundedly rational models.
So quick follow-up question on that. So when you say that there are different weights placed on every person's, you know, opinion, is it a function of how many people you're connected with, or is it a function of how much prior information the person had, right? So do experts
it's just a function of connections. So essentially the way these models work is everyone gets a signal, and the signal is equally good for everyone.
Oh, okay. All right, got it.
Since many people see my signal and nobody sees your signal,
yeah,
the beliefs of many people are influenced by my signal. Whereas your signal nobody sees, so nobody is influenced by your signal. So over time, what's going to happen is beliefs of a lot of people are going to be influenced by my signal, directly or indirectly, whereas your signal will get a very small weight.
Got it.
Okay, that's really the very simple intuition here.
Yeah, thanks.
Now, of course, it turns out that, as you can probably see, this is not actually going to be true if people are fully rational. Okay. So if people are fully rational, they will understand that this is the problem. Okay. But for them to understand this, they will need to know the network, and they will need to know who's actually got all these connections. And they will need to make all these indirect inferences. Okay. Yep. Now, so I won't actually get into this, yep. But in fact, this literature that I'm mentioning here, so especially the work that I did early with Bala in the 90s, but more recently, the work Douglas Gale and Shahar Karib, they wrote down a really, really simple model with exactly these features, fully rational learning model. And it became essentially intractable. You couldn't solve it. And so Omar Tammuz and Elkhanan Mosul, who are really mathematicians, they've come up with a number of very beautiful, very deep results in this model, okay, where you can do Bayesian updating and everything, okay. And you can show consensus, you can show, incorrect consensus. But the model is so hard that you can't pin down how much influence different people are going to have, okay, when things don't go right, okay, and so on. And they don't have really strong results on rates of convergence. So ultimately, we are interested not just in what happens, in the long run. We're interested in what happens next year, or what happens next week, right? And so for that, you need rates of convergence results, and they are typically very hard to get in a sort of meaningful way in these fully Bayesian models. So I'm already going through, the theory, but as a result of some of those arguments, people have been working with boundedly rational models. And I'm happy to take this also offline, but really the takeaway from these models would be that the rational models and the boundedly rational models, we believe that they are essentially saying broadly the same things, okay? And therefore the intuitions we have are very robust. Okay, I'll come to that in a moment. It's just that the boundary rational models are more tractable. So you can just go a lot further in understanding network effects. So you may not get the same network effects in the limit in a fully rational model, but you will get it in the rate of convergence. Okay, so somehow they are in the same space, not sort of formally, but substantively. Okay, so I'm going to be more precise. Okay, there's also a large literature on experiments. Let me move on because I'm running out of time. So, get a sense. Yeah, so used up half hour. Okay, so the model we're going to use is taken from Goyal and Kareev's paper. There are two equally likely states, A and B, and agents receive, and there will be many people, so the N is a large number, N is a set of agents. Everyone receives a noisy signal, and the signal is informative, so the probability that the signal is also binary, that it says state A is larger in state A as compared to state B. Okay, but it's noisy, it's not. So people get payoffs based on matching the state. So if they match it, they get 1. If they don't match it, they get 0. Okay. So in the first period, they will just choose their action. Okay. And that's it. So supposing you were doing this decision problem once, this is what will happen. People will just follow their signal. But now if I'm talking to people, I can talk to them and ask them, hey, what did you, I can either talk to them or I can just look at what they did. And based on what I see, I can update, my views about the true state. And then I can, if I have 5 neighbors and they all chose B, then I say, oh, well, I've got A, but it might have been just by chance. Actually, the world is really B, so I should go for B. Okay. So that's the second step. But then I see in the second period, but all my friends, have switched from B to A. So I say, oh, well, then they must have seen a lot of friends who have chosen A. So then I say, well, okay, so I've got these 4 or 5 B observations, but they've switched to A. Presumably, they have observed many A's. I've got to figure that out. Now, if I'm fully Bayesian, I'm going to have some view of the network these folks have, and I'm going to make inferences based on how many neighbors they have seen, and then update based on that. And then I will have a view about state A and B. And then I will choose an action. But then my neighbors will now know that I have made some inferences about the friends of my friends, if I've changed my actions. And this is how, in principle, Bayesian updating would work in this model. Okay. And the question is, how does the network structure shape information aggregation, and what networks lead to correct or incorrect choices? So here's some very quick summary of the theory. Okay, so we wrote down a much more complicated model in my '98 paper. Goyal and Kareev simplified it to 2 state binary action model, and they had just one signal arriving, whereas we had signals coming up through endogenous, people making choices about bandit arms. Okay, so it was a much more complicated setting. So we're really following Goyal and Kareev. So the first result they had is, in the long run, actions of individuals or their view of what the true state is going to converge, okay, over time. And secondly, connectedness of the network, which is the property that there is a path from any person I to any person J. Okay, so by that I mean I observes J directly, or I observes, X who observes Y who observes J. Okay, so and similarly J observes I, or directly or indirectly through a path. Okay. So this is a result we proved in our paper, but subsequently many others have used the same logic. Connectedness of the network implies consensus. Okay. Now turning to whether, if you have a large society, whether people will arrive at the truth. From the strong law, we know, the strong law of large numbers tells us, because signals are informative, if I just take all the signals together, I will of course get rid of the noise and I will arrive at the truth. Okay. So the question is, in a large society, will the network structure interfere with the strong law of large numbers? Okay, so it turns out, so Mosil and Tammuz have a very nice theorem. If you look at undirected networks, so an undirected network is a network where every link is symmetric. So if I observe Girish, then he observes me. Okay. So if you have undirected networks and they're connected, then in a large society, you will get complete learning. In other words, I fix n, the number of agents, and I take the limit on t, okay, that's the number of periods, I will get convergence. Now, as I take a limit with n with respect to n, the probability that I get to the correct action will get arbitrarily close to 1. Okay, so that's the complete learning result. Now, matters are very different in Twitter. So remember, in Twitter, what is really distinctive about Twitter is that it's a directed network. Okay, I follow Obama or Trump or whoever, or I follow, some celebrity. They don't follow me, of course. They don't even know I exist. Okay, so it's a profoundly different world. And in that world, so we actually proved this. I was visiting England in 1996 when we wrote this paper, and there was all this Charles and Diana affair going on. So I coined this term royal family network, which is basically a network. So you imagine a network on a circle. People hang out with their neighbors, but there is a group of people, which is the celebrity, who everybody observes. Okay, so that's the network that I'm not sure you can see, but you see what's important to note is that this is a directed graph. Okay, so I'm looking at the royal family. The royal family is not interested in ordinary folks. They're just hanging out by themselves, okay, more or less. So what we showed is that in royal family-like networks, they actually combine features of homophily. Okay, you have this local neighborhood and you have the celebrity circle. Okay, this very, very unequal network. Because, of course, the royal family, their incoming connections is the whole population. So it could be of the order of n. So it could be millions of people. Whereas each of us, of course, only has, 10, 15 people looking at us, or 100 people looking at us. Okay, so it's profoundly asymmetric. So we showed that in royal family type networks, you can have breakdown of learning, and Mosel and Tammuz showed that indeed you can show this formally in the Gale-Karib type of model. Okay, and Golub and Jackson, I'm going to come to that paper and recruit learning in a moment. They showed that similar things happen. So really, in response to Tushar's question, really what happens when you have this royal family-like networks is that the signals of the royal family get disproportionate weight. So the strong law breaks down, okay, because of this imbalance, okay, in the weights that you place. Okay, so that's the first background. So there are, as I said, there are difficulties with Bayesian updating. And so we're going to go to this de Groot model, which functions in this way. So what happens in the de Groot model is, of course, the first period, people will just follow the signal. But in the second period, they look around, they look at the signals of their neighbor, they look at the signals, or they look at the actions of the neighbors, and they choose the majority action, which is not that different from Bayes updating. But what happens in period 3 onwards, or period 2 onwards, is different, because now I don't make inferences of what my friends have learned from their friends. I don't even think about that. I just look at my neighbors and I just try and imitate the majority amongst my neighbors. Okay, so I'm not really going to think about indirect inferences along long paths of the network. Okay, so I'm just going to take a sort of boundary rational approach to it. Okay, so again, we can ask questions about aggregation and correct and incorrect consensus or breakdown of consensus in this setting. So this is a model that we've taken from a recent paper by Arun Chandrasekhar and his co-authors in Econometrica. And but the idea of averaging across neighbors really goes back to Maurice de Groot, who was a statistician who wrote this very famous paper in the 1970s. And actually, de Groot built on a bunch of number of folks who had done work in the 50s and 60s. So this is a very old strand, not in economics, but in statistics and sociology. Okay, so let me, so here's the networks we're going to be looking at. And I'm going to move on because now I'm I've used up roughly 40 minutes of my time. So I have about half hour. So let me try and give you, so what we're going to do is we're going to take a baseline classical model of decentralized learning, or decentralized networks, which is the Erdős-Renyi network. Now, many of you are, I'm sure, are aware of Erdős-Renyi networks, but let me just say that an Erdős-Renyi network is named after two mathematicians, Paul Erdős and Alfred Renyi, who wrote a series of papers on a model which works like this. There are n nodes, and there's a probability P of a link being formed between any two nodes. This probability is identical and independent across pairs of nodes. So for any node, the probability, the average degree is going to be P times n minus 1. Okay, and so when you work through this model, it turns out it will have a Poisson degree distribution. So the number of connections will be Poisson distributed. And Erdős and Renyi proved a number of very deep and beautiful theorems about the network properties of this graph. Okay, so what's interesting, as many of you will immediately realize, that the Poisson distribution of connections, it's extremely concentrated around the mean. Okay, so if the average degree is 4, that is everyone, on average people have 4 connections, that's P times n minus 1. Indeed, most people will have 4 connections, and you can check this. Of course, there are a few fringe folks with 1 or 2 links, but many people will have 3, 4, or 5 links. Okay. So we're going to use that as a baseline model. It's been very widely studied, probably the best understood network. We're going to now move from that to a homophilous network. And the way we do that is we go to what is known as a stochastic block network. And so what I've done is I've kept the average degree of the network the same. But now I have groups, and there are 40 nodes here, and there are 8 groups of 5 each. What we do is there's a probability of linking within your group, which is much larger than the probability of linking across the group. But we calibrate these probabilities in such a way that the average connectivity remains the same as in the Erdős-Renyi network. So you can see when I generate the stochastic block network, I get these communities. I get these subgroups which are much more connected within than across. So you have 8 groups, and finally, I turn to the Royal family, and really the Royal family is a network where, in this particular instance, everybody is located around a circle. But what's important is that the links are directed. Okay, so if it's a little messy, but what I'd like you to realize is that imagine that people are on a cycle, and the links are moving clockwise, and then you take 3 guys, let's say 1, 2, and 3, and you put them at the center, and then you connect everyone up with 1, 2, and 3. By that I mean 4 to 40, all of them form a link to 1, 2, and 3. Okay, so all the links coming into the Royal family are incoming links. Okay, so that's the structure. So we have our local friends, and in this instance, we have one local friend. I'm talking to the guy, let's say, on my left. I'm going clockwise down the circle, but then I'm looking at these 3 guys in the middle, and so I'm looking at myself and these 4 guys. So I'm accessing 5 signals, if you like, okay, which is what I'm doing also in the other networks. Okay. Okay, let me just pause and check if people are comfortable, with these settings. These
quick question, Sanjeev. So in this case, essentially the difference between, say, for example, the Erdős-Renyi and Royal family is that the first one is more of, a thin-tailed degree distribution, while in the royal family case, you have something like a preferential attachment process where you have these stars, and as a consequence, you have a fat tail of in-degree distribution, right?
That's right. Exactly. Yes, that's exactly right. Yeah. So essentially, the degree distribution, I mean, this is not strictly, so let me be a little more precise. So the Error-Shreni and stochastic block are classical models, and we know how they are generated. They're generated through some stochastic process. And you could generate a preferential attachment. You could generate unequal network through preferential attachment. It's a good question. So generally, so one has to be a little careful here, because in the, so this is a little stylized. The royal family is quite stylized. So you're not going to get, this local neighborhood and this as cleanly you see in a preferential attachment model. That it doesn't have this local structure. To get a local structure, you need something more than preferential attachment. You need some additional feature of linking with basically the friends of your friends, which is not a feature of preferential attachment. But so it's not quite preferential attachment. It needs more. So in particular, the royal family will have generally high clustering, which is missing in preferential attachment models.
I see.
And the clustering is sort of important because it reflects homophily. This is not going to be very important in the experiment we are running, but in practice, Twitter is a bit like that. You have a community of 30 people, who are following each other, and then they're all following the gurus, who are the royal family. So that's not really captured by preferential attachment. This local structure is missing, preferential attachment models. I mean, you can adapt it, of course, but okay. So what we're going to do is, so I'm going to set up now the theory. What we're going to do is we're going to have each of the 40 people receive signals. Okay, remember it's a binary state, so there are two states, and they will receive signals from the states. So we're going to talk about N0 as a number of correct signals. So let's say, the true state is A, then N0 is A signals. Okay, and N minus N0 is false signals. So NT is the number of correct actions made at time t. So NT reflects the guesses that people are making over time. And we want to understand how NT behaves relative to N0. Okay, so if you start with N0 correct signals, the full extent of learning would be if you go all the way to N. Okay, and so the extent to which you learn is given by the ratio NT minus N0 divided by the maximum possible learning, N minus N0. If you do learn, but of course you may go the wrong way. If NT is smaller than N0, then we're going to define it as NT minus N0, and divided by N0. So if indeed NT goes to 0, then this ratio is equal to -1. So the ratio ranges between -1 and 1. Okay, 1 refers to complete learning and -1 refers to incorrect consensus. Of course, if there is no movement at all, then CT would be equal to 0. Okay, so in a world where everybody is isolated, it's an empty network, there's no learning. You should not be doing anything other than just persisting with your signal. And so then NT would be equal to N0. Okay, so let's run through. So what we've done here is we've simulated for these networks, we've simulated the learning process with degree learning. And so what we get here is summarized here. This is 1,000 simulations. And on the y-axis, I have this the CT measure. Okay, just remember this is CT. Okay, and so I'm just plotting that. And what you see here is with the stochastic block, which is blue triangles, you really actually have, you you don't go very far. Okay, on average, you're around. I mean, you get to about roughly around 60% of the learning. But in the royal family, you get very quickly to 100% learning. And in the royal, in the Edo Shreni, you get there much slower, and maybe you don't even get there. Okay, but you're probably going to get there in the very long run. Okay. So what's the intuition for the breakdown of how am I doing for time? Okay, so let me move on a little bit. So I think you might be able to, if you think about the way the network is structured, you might be able to work your way through the logic, because the majority of people are in your community. If they're stuck in, let's say, red or action A, well, if you see one guy from outside this community, that will not be enough to overturn your opinion of what the true state is. So it's this echo chamber-like property of stochastic block that really sustains breakdown. We've already talked a bit about the royal family, but essentially you can prove that in the royal family itself is a clique, because they keep looking at each other, and occasionally they talk to one or two people outside. So they will be, they will rapidly arrive at consensus. And since everyone is looking at them, and they are a majority in the neighborhood of everyone must conform to them. Okay? And therefore you must get consensus. And so indeed, this is what you see here. You get convergence, as we were looking earlier, but of course you don't necessarily get convergence to consensus, okay, as we saw here. Okay, so this is just saying that people settle, okay, in the long run. Okay, so and then what do they settle on? Well, you see here that in the Edo Shreni, 63% of the time they get to consensus on the truth, but there's a significant number of cases where they don't get to consensus. Interestingly, in the royal family, you get to consensus in all the cases. Okay, and in the stochastic block, you get to consensus only in 30% of the cases. So in 70% of the cases, there's a breakdown consensus. Okay. So that's the these are the sort of theoretical predictions that we want to take to the experiment. So here's the first hypothesis. Individual guesses converge. The second hypothesis is that greater breakdown in consensus under stochastic block as compared to Edo Shreni and the royal family. The third prediction is that there's more correct and incorrect consensus in the royal family. Okay, you can see that here. There's more correct consensus as well as more incorrect consensus. Okay, so subjects are shown, this is the way the experiment is designed. They're shown a bag that they're told the bag contains 10 balls. It could be a red ball if it contains 7 red and 3 green balls. And it's a green bag if it contains 7 green and 3 red balls. So every subject draws a ball and sees the color. So you can see if the bag is green, it's more likely you will draw a green ball. If the bag is red, you're more likely you will draw a red ball. Subjects, so they draw the ball, of course, with replacement, so it's IID. And then they guess, and then they look at their neighbors and they guess again, and so on. So they go on for 12 periods. One period is picked randomly as a payoff relevant period. And subjects earn positive payoff if the guess matches the true color of the bag. So let me just remind you, I won't talk about the group of 10 experiment today, but the group of 40 is the one we focus on. There's a typo here. There are really 3 networks only, Edo Shreni, stochastic block, and royal family. We did run an experiment on another network, but we won't have time to talk about that today. The experiments were run in Valencia in the Linux lab. many of you, if you work on experiments, you probably use the lab. Experiment lasted about an hour and a half, and subjects earned about 19.3 euros. So this is what the screen looks like. You have me, that's the subject, and then you have the guess in the previous period, which is given by the colors of your neighbors. There are 4 neighbors. So 2 of them have guessed red, 2 of them have guessed green. And so now you have to guess, and you click on G or R, and you can click and you can go back and you can check previous guesses. Now, this is of course not, this is not relevant from a group perspective. Okay, it's only relevant if you are trying to do something more elaborate. The group person is just going to look at previous period guesses and just follow the majority. Okay, so here are the.
Sanjeev, quick question about, so in the royal family, within the royal family, is there, so what's the tie-breaking rule like? Like if suppose, they say 50-50 saying green and red, how do they reach their decision?
Yeah, so so they just randomize.
Randomize, okay.
Okay, so what's going on here is, this is the first overview, and what we see here is we see that the royal family is moving. This on the y-axis, remember, is a CT parameter, and 0 would indicate no learning, and 1 indicates full learning. We see that, that there's, you're going, I mean, you're not getting to 1, okay, but you do see the patterns that we saw in the simulations. The royal family is up there, the heterogeneity is slower, and stochastic block is much lower, okay, in terms of aggregate movement of CT. This is really more directly on the divergence hypothesis. We see that by around 10 or 11, these only 10% of the subjects are actually switching. So 90% of the subjects are persisting with the action that they took the previous period. And this is across the 6 rounds that we ran the experiment. If I look at the last 3 rounds, then the switching probabilities are significantly lower. So they haven't completely settled, but they have almost completely settled. Okay, so it's a reasonable thing for us to be looking at what they have settled on. So what does the limiting behavior look like? So this is the key slide. What we do is we look at period 7 to 12 guess distribution using CT. And what you see is in the heterogeneity, almost all the data is concentrated from 0 learning, no learning, to 1. And a lot of it is concentrated around the 0.5 point. In the royal family, what you see is this negative learning, in the sense that you get a negative CT, okay, which you almost never see in heterogeneity. And the other thing you see is there's a lot more higher learning. The CT takes on higher values, like points, there are 25 cases of probably 0.6, and then there's quite a few which are very high, which are close to 1, almost 30 of them. With the stochastic block, you see the opposite. You see a very high number of cases where you have almost no learning. Okay, it's very close to 0. Okay, so those are the limit outcomes. And let's now turn to the hypothesis 2, the breakdown. And so here we see that indeed, in line with the hypotheses, the royal family has a very little breakdown. So breakdown, by breakdown I mean you are between minus 0.3 and 0.3, okay, in that band. And you see that, you see that the stochastic block has much higher breakdown, okay, as we saw in the pictures. And we have these confidence intervals, and we'll do some regressions in a moment, and these things are all statistically significant. Okay. Robustness, we can do the same with, we had a band when there's a breakdown. We can have smaller bands, larger bands, you get the same result. The final hypothesis is on correct and incorrect consensus. And again, you see that the royal family has higher correct consensus, but also much higher incorrect consensus. Okay, and the differences are statistically significant. And so if we do regressions on these differences, so this is the robustness, but if you do regressions, these are just OLS regressions, then you see that the royal family, incorrect consensus is significant, and the breakdown is significant for stochastic block. We can run these regressions, in different ways with different bands, K 0.3, 0.2, 0.5, and we can also do logic regressions, and we get essentially the same pattern of results. So let me spend a few minutes on, maybe I should pause and ask if there are any questions at this point. So we've shown that with stochastic block community-based networks, you have breakdown in consensus a lot more than in Edo-Shreni and royal family. And we've shown that with royal family networks, you get to incorrect consensus a lot more than with Edo-Shreni and stochastic block. Okay. So are there any questions?
Can I ask a dumb one? I mean, I'm losing track of the original game here. So the original game, as I understand it, is still the bag with 7 balls. Was it 3 red and 4 green? Is that correct? And successive draws. That's what these individuals each is doing. And I'm presuming that means that these draws are taking place with replacement, right? So the probability of a red ball is always the same. Or am I missing something?
Yeah, so there are 10 balls
10.
in the bag. Yeah, there are 10 balls, but otherwise, the important thing to note is that the experiment has 12, one experiment has 12 periods. You draw the balls only at the start of the first period.
Right.
And then you guess, and then you look around at your neighbors, you guess again, and then you look around at your neighbors again, and you guess again. And your hope is that as your neighbors look at their neighbors, and the neighbors of the neighbors look at their neighbors, there is going to be some percolation of the signals.
Okay.
Through
Okay.
the path of the network.
Right. So there's not a succession of new signals based on new draws.
No, so that's across
okay.
the experiment. Yeah.
Okay.
So there are 6. Yeah. So every group plays this experiment 6 times.
Right. I understand. Thank you for that.
Yeah.
Also, how's the royal family established in this experiment? So is only that you can see the signals of a few people. So how do people figure out what makes the royal family?
Yeah. So as I said, people actually see the screen.
Yeah.
So they actually see the network.
Okay.
But they don't. They see the network and they see their location in the network, but they see the actions only of their neighbors.
Mm.
They don't see the actions of the neighbors of neighbors, etc., etc. So it must be mentioned that this is this is giving them more information than the group updating really requires. The group updating just requires you to know your neighbors. It actually doesn't. It assumes that you will not use the network information.
Yep.
Okay.
Sorry, one other quick question. Again, possibly ignorant, but when I look at your royal family network, I immediately think, well, if we're talking about the 1990s and the royal family issue, what if we have two nodes and one of those nodes is the Murdoch newspapers or something like that, right? So, and when I think about a network like that, where there are two central nodes to which most people are connected, is a case like that characterized by one of your others? Or would that be a separate and interesting case when you have a bipolar network?
Yeah, so I mean, I should say it right away that we have not really. So we don't cover, if you like, these partitioned type of societies where there's a group of people who are talking mostly to, who are observing one outlet, and there's another group which is looking at another outlet, and those two outlets may or may not be connected. They probably are, but so that would be more. Yes, that would be right. So that, so that would be more. That's right. So in this royal family, the royal family is pretty cohesive. In fact, it's a clique. They talk to each other. So they are not really opposed. In fact, they will necessarily have the same view. So you're right. That's a very good. It's a very good point. And maybe we need to think about that, I think, as another treatment, if you like, that's a very good point. Okay. So those are the network effects. And so the question here is, what rules are individuals following? Are they following something that's, what de Groot would predict? So de Groot is very easy to calibrate because I have data at for T-1, what people have done. And then de Groot will tell me, if a majority of people did green, I should do green. If a majority did red, I should do red. And if it was equal, then I should randomize. Okay. So I have the data for T-1 for every T-1 starting period, for T equals 2 onwards. And so I can calibrate de Groot. I can just use de Groot to forecast what a de Groot agent would do. And I could compare that with what the subjects actually did. Okay. So that's a thought experiment. And we want to know if most of the time people were following de Groot. So this is a summary of, if we did that thought experiment with our data, this is what we get. Okay, so of course, at the start, everybody does de Groot because everybody just follows their signal. Okay, and then people are probably learning. So they do a bunch of stuff, but then over time, by around 11, 12, they are more and more, they're closer, okay, to de Groot. So in the Eros training, it's 90% of the subjects are essentially doing what a de Groot agent would do. Okay, so that sort of raises a number of questions. How do we think about these changes across time? How do we think about the differences across networks? And so I should say that this match is better if we look not at the first 3 rounds, but in the last 3 rounds. So across rounds, there's learning and, it shows up. But then another question that comes up is, well, if they're not doing de Groot, what are they doing? Okay, so are they doing something else which is identifiable? And what we find is a possibility is that they just stick to their signal. They are entirely indifferent, to their neighbors. They just don't care about what their neighbors are doing. So we ask, given the data doesn't match with the group, how often does a player's guess in period T match with their initial signal? Okay, so this is just following your signal blindly or stubbornly. So this is what we get when we add it up. So across 3 networks, there's very high match with the group. And then when they don't match with the group, then a significant fraction of the cases, they are just they are doing things which are consistent just with their initial signal. Okay. So really, if I just look at these 2, that explains 95% of the choices. Okay, which is very very high. Okay, so I think I'm basically out of time. So let me just leave you with this summary slide. We have built on a very long tradition of work to try and understand network effects from an experimental perspective. We've looked at 2 properties of networks which are being highlighted by the empirical literature, unequal networks and homophily. And the theory has strong predictions. We've taken those predictions to the lab, and we find the subjects behave really very much in line with the theoretical predictions, and the behavior seems to be consistent with the group and following your own signal. I should say that I really like this suggestion that we could have outside outlets like media, and people may have very somehow partitioned in terms of which media sources they look at, and that could be another network that might be worth looking at. It may be different from the royal family. In fact, I think its properties might be different. But yeah, thanks very much.
Thanks a lot, Sanjeev. Very interesting paper and presentation. Since the time is up, what I'll do is I'll officially end the seminar, but I'm sure there are questions, or at least I have one. So if you have time, maybe you can take the questions.
Oh, sure, yeah, happy to.
Excellent. So I see Tushar has a question. So Tushar, why don't you go first?
So I'm sorry, I might have missed some bits of it, but I'm struggling to understand the difference between this model and, say, a cascading model where you have people who have different levels of accuracy of their signals, and some are experts, so their signals are even better. So the implications in that model would also be very similar, and I might be totally wrong about this, but the implications are very similar to the cascading model, aren't they?
So I think that really what is at issue here is the cascading model is essentially a very particular network. It's just a sequence of people, and they're observing, and in addition, everybody is observing everyone, right? So person T is observing everyone in their past.
Yeah.
There's always been this concern that it's clearly a powerful, elegant model, but it's not very clear. So, it's not very clear what's the sense in which, this is relevant for the world that we inhabit, where people are sharing information cross-sectionally. There's a group of people, they're getting signals, they're sharing information. And so information is flowing across time, but also, they're repeated. There's repeated stuff. And so somehow it's not very clear whether the results are robust to other specifications or observation structure. It's not very clear whether you need these experts. because the setting you're thinking of is exogenous experts, but here there are no exogenous experts. In fact, in these models, everyone has signals that are equal, equal accuracy. So here the network is doing the job, and these networks are taken from the empirical. So in this world, if these networks are homogeneous, then indeed you will get, all the properties of information aggregation will obtain.
Yeah.
You will not have any of the pathological outcomes of sequential learning. So these are, so this is a setting where the baseline is sort of, more classical, if you like. Yeah.
Yep. Thanks.
Ken? Ken, you're on mute.
Thank you. Let's think about something a little bit different, but maybe it's related, maybe it's not. There's all these people out there that in the forecasting business. So we've got N individuals who forecast GDP growth over the next year, say. Now, studies have shown time and time again that if we take an unweighted average of those N forecasts, that is better than any kind of weighted average, certainly better than individual ones, but it's better probably in a mean square error sense than any sort of weighting scheme, almost any weighting scheme that you can think of. So these forecasters all live in the same industry, so they talk to one another. So in that sense, they share information. What is that? Can we infer something about the underlying structure of the network, given that that finding that unweighted average is the best way to combine forecasts?
So the only thing that so I know some of this work, although I haven't been following it up, reading the literature more recently. But I was going to just say that so I imagine that this literature is very sophisticated. So they've probably looked at some information. They've looked at they've time-stamped things. So what I was not sure was the forecasts that people have they arrived at those forecasts after, if you like, talking to other folks in that industry? Because then, of course, there's some underlying network in the background. But yes, indeed, if it is the case that they have talked and they've come up with a forecast after talking with other folks, and then you do this unweighted, that seems to suggest that the network is probably fairly homogeneous. Because imagine that people get signals, some event happens, people get signals on that event, and then they stop for a bit. Now, if it was a very unequal network, very quickly, the stars or the hubs will, their opinion will dominate somehow. Okay, so one needs to be careful about, exactly the network structure, but one can see that if indeed there was this huge asymmetry, then people will have rather similar beliefs, but those beliefs will reflect disproportionate influence of a few folks. And then that should go off. It's not going to be in line with the, if you like, the fundamental value. So to that extent, what you're saying seems to suggest that the network is probably quite homogeneous. But having not read these papers, I can't be sure exactly the timing of these, the forecast that you take. Is it done very soon after some event happens, since people have not had a chance to actually interact?
No, I think they would talk to one another because because they take published forecast after the event and compare that to publish GDP growth after the event and see how those two quantities line up, the forecasts with the realized value. So it's all after the event, and they all talk to one another.
Yeah, so that's an interesting, yeah, I mean, that's, of course, that seems like a very rich setting because there are prices and there's a lot of other stuff going on. So I was wondering whether you would also get information aggregation through the prices that people are seeing. But of course, this is macro forecasting, so I don't know what exactly the role of the prices would be, but in a market setting, one would have thought that, you know, financial market setting, one would have thought that, you know, the prices are evolving and that's also reflecting lots of, but so the experiment I had in mind was, or, you know, the setting I had in mind was there's some event that's happened and people now have private signals and then they talk amongst themselves. And then they come up with a forecast, let's say the value of the firm or some growth sort of thing, and you write it down. And then 6 months later or 3 months later, you know, you look at what really happened. That very simple setting, that, yeah, if indeed it is the case of the unweighted average, that seems to suggest that, you know, people talk with a few friends. Maybe there's homophily, so they talk with people, you know, and then those things are different. There's some dispersion, but when you aggregate it, you get to something close to the truth. Yeah, the network certainly doesn't have these hubs. That seems to me likely. Or it has hubs in the setting that I think Rod was saying, that there are distinct hubs. And so, yeah, so when you put them together, you actually do get something close to the truth. It's one of, yeah.
I wonder if I could just extend that discussion a little bit. And the way you're structuring these models and the way you describe the literature suggests that there is a true state and an untrue state, and people don't actually value one relative to the other. That is, there is no utility attached to the outcome. It's just whether or not people believe one thing or the other. But what if we have a world in which it really matters to people, right? So that I really want, say I'm in a government that's currently sitting and I really want a high GDP forecast. And there are a whole bunch of people who support a government that is not sitting and they really want a low GDP forecast. So that when we're drawing these balls from the bag, there is some personal valuation we place on whether that bag is red or green.
Yes. So yes, that's right. Yeah. So
the question is, how will that make a difference, right? I mean, presumably it will, right? So that we're more likely to get a bipolar set of outcomes. People will tend to gravitate to what they want to believe rather than necessarily the truth. I'm not certain if whether a network can do that or whether that's actually a psychological question.
Yeah, so these are essentially models where you have so essentially the problem this sort of setting you're describing is really one where I want to be right. Let's say, I mean, I want to be guessing right, but I'd rather that, you know, the truth was A rather than B. So if the truth was A, I'd be a lot happier. Whereas if the truth was B, you'd be a lot happier. And so if you like, they're biased. In this model, there's no bias. People just want to match, you know, their, yeah. So of course, yes. So we haven't, let's see. So I don't think, okay, so I'm just thinking aloud here, but I don't think it's, so I wrote down models, you know, in the 90s. I have some models, presumably there are others who have written down models with this sort of flavor, but there is biases. and they will interfere with the learning process, of course.
Yeah.
Quite apart from the fact that I might want to seek to influence you because, because I might.
It's in your private
like
interest,
media.
yes, that's right.
Yeah, so quite apart from that, I think just what I do might have a different, because if I have a certain belief, I might actually choose green. With the same information, you might choose red. Just in expected terms, you might have a different response. So that could come into play. And there are some models which do that. Now, I don't know how this is going to play out. I don't think, I'm not quite sure how it will play out.
Yeah, but to capture it, I mean, the question that interests me superficially, at least at the moment, is to say, well, sure, I mean, we could introduce into your model a bias which says that if I draw a red ball, but I really want a green ball, then a greater proportion of people who do that are going to actually believe that it was a red bag rather than a green one, right? So that you introduce an explicit proportional bias into the decision process, no matter what you're told by your network, and maybe even that you know that parts of your network have particular biases as well, and you collect together with those. So, but the question is it a matter of introducing an explicit bias like that, which is sort of unexplained, right? My belief will be affected by my bias, what I want to be true. Or is there something about a network that can generate that even if I don't introduce a bias like that?
So this is very much the flavor of these network models, that they are kind of saying actually people don't have these biases, but they could get locked into situations because of the network configuration. So this is really what's happening in this homophilous network. People don't have any biases, but it just so happens that signals line up and then they get stuck.
Right.
So I like the way what you're saying is really how you would model biases in this DeGroote setting. You would need different thresholds, essentially switching from green to red. If I'm a green person, it might be very easy for you to persuade me to switch, whereas to go the other way might be harder.
Yeah.
And that should normally lead to much more breakdown of consensus.
Right.
Because you and I are looking at the same evidence, but we feel comfortable doing rather different things.
Yeah.
Sanjeev, if I may have a question. So my understanding of what you presented was that you have a high degree of breakdown in stochastic block case, and in the royal family case, you get some sort of a bimodal distribution where you have a high percentage of correct consensus, but also a high percentage of incorrect consensus.
Right.
And what I would want to know, and I think it's very easy in your case, and you can do that, is what happens if you define something of a social welfare function in terms of let's say CT is a dollar value, and what I as a policymaker am concerned about is which network gives you the maximum utility, or even the distribution of utility in that respect.
Yes. Yeah, no, so that would be very easy here, because it would just be the welfare would just be the match, the correct match, the proportional correct match. Yeah, you're right. In fact, we meant to do it and we haven't.
But it's not very obvious, no, because in the sense that if you look at the royal family, it may not have a lot of breakdown, but you have a high proportion of incorrect consensus as well. So it'll be very interesting to actually show which case in fact dominates in that sense, if you think about CT as a dollar value, because
actually what one would need to do here is actually very simple. So really what's going to happen here is all the correct matches will get value 1, and all the incorrect matches will get value 0. And so all you need to do is just weight those things, with the fraction, with the the probabilities, and that's it. So in fact, one could do it, in a couple of minutes, actually. Yeah, and you're right. It's not obvious actually what the ranking of these networks will be in terms of social welfare. Yeah, if now, of course, it would be. Yeah, so you're quite right. Yeah, it's not obvious.
It'll be very interesting to see as well, and it's very doable. I mean, I was very keen. I thought that slide will be coming, but yeah, I'm very keen to see
that's
what comes out of that.
Yeah, no, we discussed this. It's just that we just got it. Yeah, we should have had that slide. Yeah.
Excellent. Are there any questions? Otherwise, maybe this is a good point to let Sanjeev go.
So a small question about the biases that Rod pointed out. I mean, it depends pretty much on whether you think the bias is common knowledge as well, right? I mean, if I know that, my neighbor is extremely biased, then perhaps I'll discount the action that my neighbor is taking because of that reason. Or it could be the other way around. If I know that my neighbor is extremely biased in picking red balls, and now he comes up picking up a green ball or saying that it's a green ball, that's a very strong signal, right? So it depends pretty much on whether that's common knowledge or not, right? Isn't that the case?
Yeah. So I think Tony, my co-author, is I think he was. I don't know. He's still on. Yeah. So he and I, we've been thinking about this problem and over the last several months, and we've been actually trying to write down models where you have these biases, and there are these biases, and you're trying to understand who you should talk to, and you're trying to understand what you should learn from them. But that's probably the topic for another talk.
Thanks. Thank you so much.
Thank you very much.
Thanks a lot, Sanjeev, for a very interesting presentation again. And thanks, everyone.